Welcome. In distributed systems, performance and stability often depend on understanding the fundamental building blocks of our software. Today, we delve into one of the most critical of these, the executable and linkable format. We will move beyond a surface-level overview to dissect the internal structures that enable modern operating systems to load, link, and execute our compiled code. This session is designed for senior engineers and architects who need a deeper understanding of how their C++, Rust, or Go code truly operates under the hood.
By the end of this session, you will be equipped to, first, deconstruct the purpose and structure of the ELF section header table, identifying critical sections like .text, .data, and .bss. This is the blueprint of your compiled binary. Second, you will be able to analyze the process of symbol resolution, differentiating between strong and weak symbols, and understanding how the static linker resolves external references. This is key to diagnosing complex linkage errors in large-scale projects. And finally, you will be able to apply this knowledge to practical system diagnostics, using tools like readelf and objdump to inspect binary internals for performance tuning and debugging. This moves theory into practice, providing tangible skills for your role.
Let's begin with the core layout. Every relocatable and executable ELF file contains a section header table. Think of this table as the file's index or table of contents. It is an array of structures, where each structure points to and describes a section within the file. The ELF header itself contains a pointer to the start of this table. Why is this important? Because it allows tools like the linker, the loader, and debuggers to find the specific pieces of information they need without scanning the entire file. Several sections are fundamental. The .text section contains the actual compiled executable machine code instructions. The .row data section holds read-only data, such as string literals. The .data section contains initialized global and static variables, while the .bss, short for block started by symbol, holds uninitialized global and static variables. The operating system's loader allocates memory for .bss at runtime but doesn't need to load anything from the file, which is a key optimization for binary size. Other critical sections include .symtab, which contains the symbol table for linking and debugging, and .strtab, the string table. You can inspect all of this directly using the command readelf-sections on any object file or executable. This provides a precise map of your binary's memory layout before it's even loaded.
Now, how do separate object files become a single executable? This is the job of the linker, and its core task is symbol resolution. A symbol is essentially a named reference to a variable or a function. When you compile a single source file, say main.c, it might call a function defined in another file, like helper.c. The compiler generates a relocatable object file, main.o, with an unresolved reference to the helper function. The linker's first job is to scan the symbol tables of all input object files, main.o, helper.o, etc., and build a global map of all defined symbols. It differentiates between strong symbols, typically functions and initialized global variables, and weak symbols, which are uninitialized global variables. The rule is simple. Only one strong symbol with a given name is allowed. If multiple weak symbols exist, the linker picks one. This mechanism allows for features like library function overriding. Once the map is built, the linker iterates through each unresolved reference and matches it with a defined symbol from its map. This is symbol resolution. If it cannot find a definition, it produces the infamous undefined reference error. Let's test this understanding. Question 1. What section holds uninitialized global variables? That is the BSS section. Question 2. If two files define a global variable, int myvar equals 10, what will the static linker's response be? Short pause. It will raise a multiple definition error because both are strong symbols.
To summarize, we have explored the critical internal structures of the executable and linkable format. We learned that the section header table is the fundamental map of a binary, delineating code, constants, and data. Understanding sections like .text,
.data, and particularly .bss, is essential for optimizing binary size and load times. We then dissected the process of symbol resolution, the linker's mechanism for weaving together multiple object files. The distinction between strong and weak symbols governs how definitions are merged and is a common source of complex build errors in large systems. Armed with this knowledge and the utility of tools like readelf, you are now better prepared to diagnose low-level bugs, optimize application performance, and architect more robust systems. Thank you.